is an attempt to describe the physics of why an arrow with high FOC may penetrate better into animal tissue, and when that penetration may be enhanced by high FOC. The usual explanation that you hear has something to do with lever arms. I'm going to quickly talk about why that explanation is not a good reason for that. And the main reason is because we have a poor working definition of what a lever arm is. So most people think of the lever arm as being the length of whatever object you're rotating. So assume here that we have some sort of long pipe or shaft, and it's pinned down here in the corner, and so we're rotating it. It has a particular length. That length can be described by a vector of radius r, and we apply a force to it. Now, there's the normal way you would do this if you were using this, for example, as a wrench to try to wrench a bolt or something here. You would push this force perpendicular to this arm. And in that case, the lever arm and the value of r, as we'll see, are actually the same thing. But when we don't have a perpendicular force, if we're applying the force in some other direction than perpendicular to the length here, then the torque that's applied here, the torque, which we typically give the symbol tau to, particularly here the magnitude of the torque, is going to be the magnitude of the force times this radial distance r times sine of theta. So theta is the angle between the radius of the radial vector that we're using to describe the length of this object and the applied force. So we have an angle here, that's this applied theta. Sine is just the standard trigonometry function. Just let me remind you what that is in case you've forgotten. If we have some angle theta here for a right triangle, if we have a length x here and a length r here, then the sine of theta is just going to be equal to x divided by r. That's going to be important for us later. And so what we actually do to describe the lever arm, which is actually this piece right here, this piece is called the lever arm. To describe this, let's construct a right triangle. And what we're going to do is we're going to work backwards from the direction of our applied force in a straight line. And then we're going to look for a perpendicular back to the point of rotation. So some perpendicular that looks like this. So this is a perpendicular here. And you'll note that there is an angle here. It's the same angle as this angle theta. It's the same angle. Intersecting lines like this have the same angle on one side as on the other. So this angle is identical to this angle. And so this length here, this length, which I'm going to call L, is basically the same thing as x over here. Here's my angle theta. So if I write down that sine of theta is equal to the hypotenuse, which in this case, again, is r divided by L. Sine theta equals, excuse me, I did that wrong. Let's try that again. My apologies. It's the opposite over the hypotenuse. That's L over R. Let's try that again. And then we multiply through by R sine theta equals L. So we see that this length L actually is the lever arm. So it's not the length of the bar that's the lever arm. It's this length here. And this length depends on this angle. As we change the angle, we change the length. So for example, if we draw our bar again, if we apply this angle perpendicular, then that is the perpendicular distance back to our point of rotation, and that's r, which is just going to be equal to the lever arm. If, on the other hand, we have a system like an arrow, okay, so the usual explanation again is we have some kind of arrow here, which I will very crudely draw, and we'll denote the midpoint of the arrow here, and the front of center position is somewhere in front. So I won't explain how to calculate FOC. You guys should be able to do that. But the FOC is here at some point between the head and the midpoint of the shaft. And the usual argument is that if you shorten this, you shorten the length of the lever arm, and that's what causes an increase in penetration. And that's simply not true. Why? Because the force of impact is basically directly into the head of the arrow. And so if we try to see what is sine of 0, this is 0 degrees or 180 degrees, depending on how you look at it. Both of them have the same value of sine. Sine of 0 or 180 is 0. So r times sine theta, the lever arm, is 0. There is no lever arm here. And that should make perfect sense because we don't have any force being applied perpendicular to the broadhead. Now, this is completely different for stabilization of the arrow in flight. We're talking about two different things, penetration versus stabilization. For the arrow in flight, the basic argument is that when you have crosswinds like this, or when you have an arrow that comes out of the bow sort of at a side angle, it's poorly tuned, then the idea then is there is some directional force pressure from air resistance that is perpendicular to the length of the shaft in either of those cases. And in that case, the lever arms do play a role, and that is what helps stabilize the arrow in flight. So we want to separate the effect of FOC into two categories. What happens as the arrow's flying through the air, and what happens as the arrow impacts. And there's nothing to do with the impact of the arrow for penetration that has anything to do with the lever arm. Impact is going to have very small angles. If your impact angle is well, the force here is a vector, and that vector is going to have its direction based on the fact that the velocity of the arrow is moving this way. So the lever arm here is just 0, and this is not the reason why arrows with high FOC may penetrate more than arrows with lower FOC. So let's try to analyze this from a different means. So here's what we're going to do. We're going to go back to very classical physics. So very simple Newtonian physics. There is algebra here, but this should be pretty easy to follow for everyone. So let's take an arrow. We're going to look at what happens at the bow first. So let's think about what's going on at the bow. And we're going to break the arrow into two parts. This is a standard trick that we'll think about the arrow in two parts. We'll think about the head of the arrow, and we'll think about the shaft of the arrow as being two different entities. Yes, there's going to be an insert. There's going to be some other things here, but for first approximations, we can think about the shaft being glued to a head. The shaft is pushing the head forward. This is a good approximation to the way that an actual arrow behaves. So we have the mass of the shaft here and the mass of the head here, and the only external force applied will be the force of the bow acting on the knock end and driving the arrow forward. All right, so then the question is, what can we do with this? So let's break this into two parts. We're going to use Newton's law. So Newton's law, F equals ma. The important point to make here is that the acceleration of the shaft and the acceleration of the head are the same. Otherwise, the head goes flying off at a different rate, a different velocity than the shaft does, and the thing falls apart. So because they're one body, then acceleration is the same in both cases. So let's calculate what the acceleration is for just the shaft. And using Newton's law, what we would do is sum up all the forces. So first we have the force of the bow. That's acting this direction. But we're pushing against the head, and the head is pushing back. So there's actually a force acting backwards here. Let's call that force little f. So we have the force of the bow minus this contact force with the head, and that must be equal to the mass of the shaft times the acceleration. So that's the acceleration of the whole arrow. This is the mass of the shaft. So this is the force acting just on the shaft, equals the mass of the shaft times its acceleration. Now, by Newton's third law, we have an equal and opposite little f acting to push the head. This is the force applied by the shaft onto the head and to push it forward. And so we can say that Newton's law applied to the head is F is equal to the mass of the head times the same acceleration. So here's what we're going to do. We're going to solve both of these for A and then set them equal to each other. It's the same acceleration, again, because if it weren't, then the head and the shaft would be separated from each other after being fired from the bow. So what I'm going to do is divide both sides by ms for this equation. Again, this is the mass of the shaft, and this by mh. This is the mass of the head. Now, this is equal to this because they both equal A. And so let's write that down. So what we have is, I'll write this here, we have that the force of the bow divided by the mass of the shaft minus the contact force between the shaft and the head divided by the mass of the shaft is equal to the contact force divided by the mass of the head. So what I'm going to do is move this to this side. In fact, the way I'll do that, I'll add this to both sides of the equation. So this becomes a plus and this becomes an equals. And then I'm going to put these two, to combine these two factors and see what we get. So the first thing is, if I want to combine these, I get a least common denominator. So I'm going to multiply this by mh over mh. So that would be mh, the mass of the head, times this contact force, plus the mass. Do the same thing here. Multiply this one top and bottom by ms, mass of the shaft times the contact force, all divided by my common denominator now is msmh. All right, the next thing to do is factor out the F and recognize that this, the force of the bow, divided by the mass of the shaft is equal to this, and there's a division by mass of the shaft in both cases, so I can actually cancel those out. So what I get is the force of the bow is equal to, I'm factoring out the F, so what I have is the mass of the head plus the mass of the shaft divided by the mass of the shaft here was canceled, so the only thing in the bottom here is mh, and that's going to be multiplied by the contact force F. And then last, I'm going to solve for what is this contact force. So the contact force, the force between the shaft and the head, what is that? That F is the mass of the head, multiply both sides by mass of the head, and I'm going to divide both sides by mass of the head plus mass of the shaft, but that's just the total mass of the whole arrow. Mass of the shaft, mass of the head put together, that's just your arrow mass. So I'm just going to call that mass total. And we multiply that by the force of the bow. All right, so what does this equation say? It says that the contact force between the head and the shaft is basically proportional. This is unsurprising. It's proportional to the percentage of the mass that's in the head. So if we take the mass that's in the head, divide it by the total, that's the percent mass that's in the head, and then multiply that by the force of the bow, it basically tells you what percentage of the force of the bow is distributed to the head and what percentage of the force of the bow results in the acceleration of the shaft here. So this is this contact force. All right, now, so why did I do that? Let's zoom in on the shaft. So on the knock end of the shaft, we have a force of the bow being applied. And by Newton's third law, on this end of the shaft, we have the little contact force F being applied by the head. This is a compressive force. So the way that you calculate the compressive force, I'm not going to prove this. You can do this with some integral calculus. But what the compressive force here is going to be given by the average of these two forces as long as we have a uniform shaft in between the two forces. So what is that going to be? That's going to be FB plus little f divided by 2. That's the average of those two forces. Let's clear a little bit of space and let's calculate what that compressive force is. So what is the compressive force for our arrow shaft? All right, so we have that FC, the compressive force, the compression on this arrow shaft, is equal to FB plus, and we'll call that over 2, plus, now what is little f? Little f is mh over mt. We have another 2 here that we have to account for, so that's mh over twice mt times fb. So this is the force of the bow. It's common to both terms. We can factor it out. So that's what we're going to do. And so the next thing that we have is that we have 1 over 2 plus mh over twice mt all times the force of the bow. So this is our compressive force. And I'm going to do a little bit more here. I'm going to put these two terms together by multiplying top and bottom here by mt. And I'll put these two terms together, and what we'll get is that the compressive force is equal to the total mass plus the mass of the head divided by twice the total mass times whatever force the bow imparts on the whole arrow. Okay, so this is basically the draw weight of your bow. So your bow is an extremely non-Hookean spring, and its maximum force applied is essentially the draw weight of your bow. And so that's what this is, and we could calculate the compression force acting on a shaft through this equation. Excuse me. Now, I don't really care about this compressive force per se because it's going to depend on bow weight. What I'm more interested in is, can we calculate the difference between two compressive forces as we change the ratio of the head mass to the shaft mass? In other words, if we're looking at the ratio of the mass of the head to the mass of the shaft, this is what FOC actually crudely measures, right? The heavier your head is and the lighter your shaft, the farther forward your FOC is. And vice versa. The heavier the arrow shaft, the lighter the head, the farther back the FOC is. So let's calculate what would be the percent change in this compressive force if we keep the total mass fixed, but change the ratio of the mass of the head to the mass of the shaft. So let's see what we get there. So what I'm again going to have to do is clear some space here to work. All right, so to calculate a percent difference, what we do is we would say the the compressive force for a test arrow minus the compressive force for some standard arrow. So we'll choose an arrow as our reference arrow, and that will be our standard or reference arrow, and we'll compare test arrows against that. And to obtain percent difference or fractional difference, we divide that by FCS. So for an instance, suppose our test arrow with our test bow had 100 pounds of compressive force. And our standard arrow had that, and our test arrow had 50 pounds of compressive force. So 50 minus 100 would be minus 50, divided by 100 would be minus 0.5. You would multiply that by 100%. That would be a 50% decrease in the compressive force. So this is the equation to calculate percent difference between our test arrow and our reference or standard arrow. All right, so let's just plug this into this equation. So what we get is, let's see here, we have MT plus MH divided by twice MT. All right, that's going to be times the force of our bow. Now, the mass total we're going to keep fixed. So our two different arrows, our reference arrow and our test arrow, will have the same total mass, but they'll have different masses of their heads. So I'm going to add to the subscript here that this is the test mass head, the test head mass. And then we're going to subtract from that this exact same thing, the total mass plus the head mass, but now this would be for our reference or standard arrow, divided by twice the total mass. Again, the total mass is the same for both our test and reference arrow. We're just changing the ratio. So we are increasing the head weight and decreasing the shaft weight by presumably going to a lighter spine or going from perhaps a heavier arrow, like a wood arrow, to a carbon arrow or something like that. And again, we're going to multiply that by the force of the bow. And then we divide it by exactly this exact same thing. So that would be MT minus MH, comma S, divided by twice MT times FB. So there are some things that are common to all these terms. The force of the bow cancels out. Twice the mass of the head cancels out. So basically all we have left is MT plus MHT minus MT plus MHS, and then down here MT minus MHS. Note that the MT minus MT is also going to cancel out. And so what we actually get with this is the mass of the test head minus the mass of the standard head divided by the total mass of the arrow plus, excuse me, this should have been a plus here. That was supposed to be exactly the same thing as this was, and this is a plus. Plus the mass of the test head, or excuse me, the standard head. All right, so this is our expression. Let's write that down. Let's recopy that and see what it tells us. So we've derived everything that we need to so far. This is, again, very mathematical, but it's physics. So what we have is that the percent difference in compressive force, we're looking for the percent difference in compressive force, that's going to be the mass of the test head minus the mass of the standard head, and we are going to divide that by the mass of the test head plus the mass of the standard head. Excuse me, the mass of the total arrow plus the mass of the standard head. Now we have to multiply this by 100% to turn it into a percentage. So this is really interesting. It says that for a given bow with a given total mass arrow, this is the formula that we use to calculate how, as we change the head of the mass, the mass of the head, how that changes the force of compression on the arrow shaft. All right, so let's do some examples. Let's clear this bit of algebra off. Let's do some examples and show how this works. So the first thing we have to do is choose a reference arrow. I'm going to choose what's kind of a popular arrow weight nowadays amongst the moderately heavy crowd. Let's choose as our example arrow, as our reference arrow, let's choose an arrow that weighs 580 grains. So the total arrow mass is 580 grains. And well, if the total mass is 580 grains, let's choose a 125 grain head. Now this will include everything in the head. This would be insert head, everything. And so this actually ends up being a really heavy arrow shaft, something like 15 grains per inch. So maybe some aluminum or perhaps a wood arrow of some sort. But for a 30-inch arrow, this is a pretty heavy arrow. This would have, according to the gold tip FOC calculator, this is going to have roughly 16%. Excuse me, not 16. A roughly 9.5% ish FOC. So if we built an arrow that basically was 125 grains up front, as people say, and 580 grains total, it would have roughly 9.5–10% FOC, and that's our reference arrow. Now, first, let's check what happens when we have a 200 grain head. So what we're going to do is we're going to increase our head weight to 200 grains, and we're going to have to decrease our shaft weight to 380 grains. And so this is going to move the FOC forward. In fact, with a 200 grain head, the gold tip FOC calculator says that this should have approximately a 16% FOC. Again, these are not exact because they don't include knocks, they don't include veins or fletchings of any kind. These are just rough estimates, but this just kind of gives you an idea as we go from something like a 10% FOC arrow to a 16% FOC arrow, what happens to the compressive force on the shaft of the arrow at launch when we're firing the bow. Okay, so we're going to use this equation. So the mass of our test head is 200 grains minus the mass of our standard head, which is 125 grains. And we're going to divide that by our total mass, which is 580 grains, plus the mass of our standard head, which is 125 grains. Of course, we need to multiply this by 100% to get our actual percent difference. And what we actually get here is plus 10.6%. So what does that mean? That means there is a 10.6% increase in the compressive forces, which I'll label as FC, and the compressive forces on the arrow shaft at launch. This is, of course, why you have to go to a stiffer arrow when you increase head weight. As you go to increasing head weight, for the same bow, for the same arrow mass, you're going to get a significant increase in the force acting on the arrow shaft, which is going to cause it to buckle or deflect more. And that will, of course, lead to a poor tune, and so you have to adjust for that by increasing the spine or stiffness or shortening your arrow or something along those lines. Let's do another example just to kind of show the effect for a more extreme FOC. So what if we go to a 300 grain arrow? That means we have 280 grains in the shaft. Again, according to the gold tip FOC calculator, that is a roughly 24% FOC arrow. And so again, we're going to do the same calculation, 300 minus 125. We're comparing it back to our reference arrow, divided by 580 plus 125, and then multiplied by 100%. All right, what does that give? Let's see, that gives a 24.8 plus 24.8%. So again, a 25% increase in the compressive forces on the arrow shaft going to this heavier front of center, higher mass head, keeping the total arrow mass the same, moving the FOC forward and increasing the head weight and decreasing the shaft weight. So this is, again, of course, why we have to increase the stiffness of our arrows. If this test arrow were perfectly tuned, and we somehow were able to lower the weight of the shaft and increase the weight of the head without changing the spine, if that were possible, then what we would end up with is a very out of tune arrow, because we would have a much higher compressive force on the arrow shaft. It's going to deflect more coming out of the bow. You're going to get a lot more dynamic reaction, and you're just not going to have a tuned arrow. All right, so this is what happens at the bow. It's important to do this because what happens at impact is similar to this, but different enough that it was worth going through this exercise. So what we're going to do, and I'll do this rather quickly as I can, is to reverse the process. So now I've got my head here. There's the mass of the head. Here's my arrow shaft. Again, that's the mass of the shaft. Now our force is an impact force, Fi, and this is the arrow actually hitting the target. Okay, so we'll do the exact same calculation. So once again, what is the force on the head? Well, the force on the head is the impact force as it hits the target, but also the force exerted by the shaft on the head. So there's a force acting this way. We'll call it little f. The total force acting on the head is the impact force minus this force here, times the mass of the head times the acceleration. This is, again, just Newton's law. Now, what about the shaft? The shaft, we have, by Newton's third law, we have an equal and opposite force. So this is just going to be F now with a plus sign instead of a minus sign, is equal to the mass of the shaft times the acceleration. We do the exact same thing. We have solve for A in both equations. And then we set these equations equal to each other. So let's do that. What we would end up with is the impact force divided by the mass of the head is equal to, I'm going to move this to the other side of the equation, and I will get F over the mass of the head plus little f, the contact force, over the mass of the shaft. We'll do the exact same thing. Factor out the F, combine these terms, and cancel MH. And what we end up with is that the impact force is going to be equal to the mass of the head plus the mass of the shaft divided by, it's the mass of the head that's going to cancel this time. So this time it will be divided by the mass of the shaft all times F. Again, notice that this is the total mass of the whole arrow. And so we can solve now for little f, the force acting on the shaft, and that's going to simply be the mass of the shaft divided by the mass of the total arrow times the impact force. Right? So that's the force acting on the arrow. On the shaft. Now, here's something that's interesting. This is a little different than what we saw on launch of the bow. Here we have the impact force acting in one direction, but we have no force acting in the other direction. There's no force pushing the back of the arrow when it impacts the animal. This is just in free motion. There's no force acting on the arrow shaft in that direction. So once again, we can calculate the compressive force, but it's going to be easier this time. Why? Because it's the force acting on either end averaged. Okay, well, the force here is little f, the force here is 0, and the average of those two is just f over 2. So we end up with f over 2. Well, here's f, so that's just going to be the mass of the shaft divided by twice the total mass times the impact force on the arrow itself. All right, so this is a simpler equation than what we saw for the previous example. We'll do the exact same thing. We're going to calculate the percent difference. And so how do we do that? Remember, that is just going to be the compression force for a test case minus the compression force for a reference or standard arrow, and divide that by the compression force for a standard arrow. We'll start to make some substitutions here. Let's see what we get. So we have the mass of the shaft for the test arrow divided by twice the total mass times the impact force, and that's this term. Then we're going to subtract the mass of the standard arrow divided by twice the total mass, and I've run out of room here, but this is multiplied by, again, the impact force. And then we're going to take this and divide it by FCS, excuse me. Well, let's copy that. What is this? That is the mass of the standard arrow divided by the total mass times the impact force. Just as before, a lot of things, twice the total mass. A lot of things cancel out. Twice the total mass in the bottom cancels out. The impact force cancels out. We're going to assume the impact forces are identical between the two arrows. And we have MST minus MSS over MSS. So what we end up with, let me again clear some space here. That the percent difference in the compressive force acting on the shaft is going to be equal to the mass of the shaft for our test arrow minus the mass of our shaft for our standard arrow divided by the mass of our shaft for our standard arrow, all times 100%. So this is now what happens when we have impact. So notice the equation is different, and the reason the equation ends up being different is because for the arrow under launch, we have the mass of the head exerting a contact force back on the arrow shaft, and so we have forces from both sides. In the arrow on impact, the only force acting on the shaft is the contact force from the head. There's no force here pushing on the back of the arrow. By the way, this is one of those reasons why many of the thoughts about how FOC works to increase animal penetration don't work. They think about the shaft pushing the head through the animal or something like that. That's not what's actually happening. So anyway, let's look and see what we get here. So again, let's use the same reference arrow. So our reference arrow had a total mass of 580 grains. That means that if it has a 125 grain head, which was our reference head, then the shaft must be 455 grains. Again, the FOC of this particular arrow is about 9.5%, something like that, according to the gold tip calculator. All right, so let's see what we get out of this when we go to our test arrows. So for our test arrow, we're going to use a 200 grain head, which means that we have dropped to a 380 grain shaft. The FOC of this was, again, about 16%. All right, let's plug things into our equation. So we have for our test arrow a 380 grain shaft, minus for our reference arrow a 455 grain shaft, divided by for our reference arrow a 455 grain shaft, all times 100%. And that actually comes out to be minus 16.5%. So what does that mean? It means we have a 16.5% decrease in the compressive forces acting on our arrow shaft when we go to our test head versus our reference arrow. So our reference 9.5% FOC arrow has significantly more compressive forces acting on the arrow at impact than our test head does. Let's go to our 300 grain test head. So 300 grains. And that would be a 280 grain shaft. And again, that arrow corresponds to a roughly 24% FOC. I think it was 24.3% or something like that FOC, roughly 24% FOC. And so now again, do the same calculation, 280 minus 455 divided by 455 times 100%. And what does this equal? In this particular case, it equals minus 38.5. So in this case, we had a 38.5% decrease in the compressive forces acting on the arrow shaft. So what does that mean? So if we take an arrow shaft and we compress it from both ends, what happens to it? Well, it buckles. That's where the oscillations start for the arrow shaft. And notice that the effect here is actually compounded. The reason that I went through at the bow case, if you're going to shoot this 300 grain head, 580 grain arrow with a high FOC, 25% FOC, if you're going to shoot that, then notice in order to do that, because the compression happens at the bow is increased, you're going to have to go to a really stiff arrow, much stiffer. You'll have to drop it at least one spine, maybe two, maybe trim the arrow a little bit. You're going to have to do something to increase the dynamic stiffness of your arrow to tune it. So not only with high FOC are you getting an increase, a significant decrease in the compressive forces acting on the arrow shaft, but you're also getting a stiffer arrow shaft to begin with because you had to stiffen it to tune your arrow. And so those two things combine to give a much smaller dynamic response on impact with a high FOC arrow. In other words, a high FOC arrow goes into an animal more straight. It doesn't buckle as much, and and therefore it has the potential to penetrate better than a low FOC arrow. Now, where does this matter? Remember, all of these things are percentage decreases in the compressive force, and the compressive force was proportional to the impact force. So if you hit a soft portion of the animal, let's say you get a nice clean broadside shot, you maybe get into the rib cage but don't hit any heavy bone, then the impact force is going to be very small. So a 30 8% decrease in a really small force is not going to make any difference. And this is the reason why it's a little bit silly for people to think that increasing your FOC has a major impact on penetration potential when you have a good hit on an animal. The Ashby reports don't even indicate this. Ashby gives no data that I have seen, and I've combed through the reports. He gives no data indicating that there is any increase in potential, any increase in penetration when no bone is encountered on the shot. And this reflects the experience of many, many archers, for particularly North American game and whitetail hunting in particular. If you have a good hit on a whitetail, then increasing your FOC is really not going to do a whole lot for you on the penetration side, because the point of increasing FOC is to mitigate the impact force and how the impact force compresses or results in compression of the arrow shaft, which results in it bending. If the impact force is small, the arrow is not going to bend anyway. It's going to just go straight through, and you're not going to get a lot of that dynamic reaction, what I think some have called impact paradox. You just don't get that if the arrow just goes straight through the animal, encountering very little impact force or resistance as it moves through the animal. It's just not important. On the other hand, if you're shooting Cape buffalo and you're going through very, very thick hide, muscle, and then extremely tough ribs, which are much thicker than those in North American game, well, then your impact force is going to be really large. And so having a really high FOC is extremely useful to mitigate that impact force and to therefore potentially increase your penetration, because the arrow will not be entering the animal with a big bend in it as it's undergoing compression through these compressive forces. So that's what's actually going on with FOC. Another important thing to point out is it's not really the FOC that measures this. It's really the ratio of the mass in the head to the mass in the shaft. Yes, the FOC sort of is an indicator of that ratio. Obviously, if you increase the mass in the head and decrease the mass in the shaft, you're going to increase FOC. But it's not the actual location of the center of mass. It's not the percentage FOC of your arrow that is directly correlated to this effect. It's really the ratio of your head weight to your shaft weight, or your head mass to your shaft mass, that's important. And this also indicates, if you go back and look at the other equations that I derived in the process of calculating these percent difference equations, you will see that the effect really has no limit. The closer you get to zero shaft mass and the closer you get to all of your mass being in your head, the more these percentages change, and eventually you get to 100% when you have, for instance, if we look at this equation here, if the mass of our test arrow is 0, if we go to some sort of hypothetical massless arrow shaft, then what we end up getting is effectively a 100% decrease in the compressive forces. That's pretty obvious. If there's no arrow shaft there, it can't be subject to any forces. So this is why Ashby sees an increase in his penetration potential when constantly increasing his FOC. It's not the FOC that matters. It's the fact that the ratio gets closer and closer to 100% head mass and 0% shaft mass. Of course, that's impossible to achieve, but the farther you go, the better things get. Assuming, again, that you have a significant force of impact. As I said, if your impact forces are small, if you are hitting an animal in where there is no large bone, then FOC really does not play a role in penetration. That's not to say it doesn't matter for arrow flight. As I said, arrow flight is a completely different thing that we may do a video on in the future. But this is the real reason why increasing your FOC could increase your penetration potential, again, assuming you have to go through something hard to get to the goodies.